So the first two problems today come from a learning objective that wants us to look at the properties of exponents that you learned yesterday in yesterday's video and apply them. That's going to be the first two problems. So how do we do this? Now, before I get started, I also want to add one more thing. There's only 8 different problems that I'm going to cover in today's lesson, but it comes from 4 different or unique learning objectives. And for many students, probably even including me if I was a high school student at the time, it may be useful for you simply to watch me go over the problems in the next half an hour and then take time to rewatch the video I'm creating and to write down the problems. One, writing down problems and seeing them again on paper as you write often kind of triggers it in your brain a little bit better understanding. And sometimes seeing it for the second time will also help you to better understand it. So make a decision for yourself what you want to do, but that is my suggestion for a lot of you. Watch me go through the first 8 problems and then go back and watch the video and rewrite them to better understand it. How am I going to use properties of exponents to show or prove these two are equivalent? Well, I'm going to start by covering up the right-hand side. And so I'm looking at the left-hand side. And when I do this, we learned yesterday that we always are going to solve this expression by looking at the denominator of the exponent. So I put a 3, and a common mistake students make is they rewrite it like this. And what they forget is that this 3 is on the bottom. To show it's on bottom, I'm going to put a 1 on top. And you may be thinking, well, mathematically, is that right? Well, 1 times 4 is 4, and then 3 is on the bottom by itself. When you multiply fractions, the 4 doesn't get multiplied by the top and the bottom. It's only ever by the top. 1 times 4 is 4, 3 is on the bottom. When you evaluate this, it's kind of like when you think of it, is there rules like PEMDAS? And there are rules. So first we're going to do whatever's in the parentheses. Remember, PEMDAS says parentheses first, and it says exponent second. So we do the inside first. So using this table that I asked you to write down, if you have not done that, the table was created in yesterday's video. It's the very beginning of yesterday's video. You may want to go back and write that down if you haven't done so at a later time. And the table is going to help us to evaluate this. So we're going to go to the column that has a 3, and I'm going to find in that column with a 3, is there an answer of 64? So I find column 3, and I go down to see, is there an answer of 64? And there is. Well, how does that help me evaluate this? So I go to 64, and then I go straight across, and I can see that it evaluates to 4. What this mathematically means is what times itself 3 times equals 64? And the answer is 4. 4 times 4 times 4, 3 times equals 64. So this portion equals 4, and then I bring down the 4 up top. 4 to the 4th. Well, sure, you could use a calculator, you can multiply by hand, or find 4, and we want to go 4 to the 4th. This is first, second, third, and 4th. Correct answer, again, 1, 2, 3, 4 is 256. I'm going to do the same on the right-hand side using properties of exponents. First step is I always evaluate the bottom first. So it's not just 4 to the second, it's 4 to the 1/2. It's always the 1 on top when you separate and move the top outside. And then again, how can I use the table to evaluate this? Because this means what times itself 2 times equals 4. So if you know the answer is 2, awesome. If not, I go to the column that has a 2, go to the column that has a 2, and go straight down until you find 4. And the answer just happens to be 2. So this equals 2, and now I'm going to apply it with the 8. This means 2 times itself 8 times. 2 times 2 times 2 times 2 times 2, 8 times. Again, could you use a calculator? Sure, but they want us to use properties of exponents. So 2 to the 1st, 2nd, 3rd, 4th. I can see I'm just doubling it each time, doubling it each time. So here's 2 to the 6th, to the 7th, to the 8th. I just showed or proved that the left side is equal to the right side. A common mistake in students is they write this down and they go, oh, 256, write this down, oh, 256, see, I just showed, they're equal. They want us to show step by step. How do we get it? Step by step is using the properties of exponents. Can you go into the chat for me right now, just so I have an idea, and can you give me, please, a 1 through 5 and how well you understood that? Again, never be afraid to give me a 1 or 2. Just try to give me an accurate understanding of how well you understood that problem. Okay. Mostly 4s and 5s, a couple 3s. Thank you for your feedback. Number 2 is very similar. We're going to use properties of exponents. The question is which step was an error created, and then how would you correctly evaluate this expression? I find that even though this doesn't seem very complicated, when I've quizzed students on this type of problem, and you do have problems like this on your unit exams, it's really common that mistakes are made. So here's how I think you can kind of bypass making those mistakes. Take whatever step 1 is and write it off to the side. And instead of trying to figure out their mistake, let's just do the problem ourselves and then compare it to their work. This is a square root. Yes, it's a radical because square roots are a type of radical. And so you learned yesterday that this is a square root, which means there's actually a little 2 here. Well, why didn't they put a 2 there? Because mathematically, when you don't see an nth root, it's a 2, not a 1, it's a 2. And also, by the way, this can be rewritten like this. That 5 can be inside or it can be on top. It is your choice in how you write it. Okay? All right, so anyways, so here we go. And so what I'm going to do is I'm going to take this and I'm going to rewrite it. And I have the 2, the nth root always goes on the bottom. And whether the 5 is inside or outside, it always goes on top. And a 1 is up top. Okay, what does this mean? It means what times itself 2 times equals 16. So 2 times, I come into this column, I go down till I find 16, and the answer is 4. You may be asking yourself, can't I just do that in my head? Absolutely, I'm just showing you how to use the graph to get the answer, or the table. Okay, 4 to the 5th, so I find 4 to the 1st, 2nd, 3rd, 4th, and 5th. 1,024. I look at my steps. I believe that I've correctly answered this. Now I'm going to compare. Okay, so that's step 1. Okay, that's fine. Here's step 2. Well, step 2 is just rewriting it. Okay, good. Step 3, they bring the 5 out. Okay, here's the major mistake, and it's a really common mistake. They forgot to put a 1 on top of the 2. So the mistake was made in step 3. Now, what should be the correct answer when we evaluate it? 1,024. Okay, if you can go into the chat right now, so that is the first learning objective. I know that you haven't practiced it on your own, but just your understanding by watching so far. Can I have right now a smiley face means I feel pretty confident I could do problems like this. A frowning face means I'm feeling confused. I'm unsure if I could attempt to do a problem like this on my own. Thank you for those that continue to provide me with the feedback. Okay, so I will share with you that number 3 and number 4, students in previous classes, the feedback I received from them was they felt really confused. So this may be part of the video that you're going to want to go back and rewatch. So number 3 and number 4, the learning objective is we want to rewrite this in a different form and then make sure we simplify. So we're going to rewrite the radical expression. Radical we can see, expression means there's no equal sign. So rewrite the radical expression and then simplify when possible. Okay, so the first thing I have to do is I'm going to cover up this so there's less confusion there. First thing I do is I have to make sure, do I have the same nth root? That means is this little number out front of the radical, is it the same? And if it's the same, we can proceed. Tomorrow we'll learn what do we do when there's adding and subtracting. Today we're only going to do multiplying. So when it's the same, I can proceed. So I start with any number that's out front. It's kind of like if I had 2x times 3x. You go, okay, 2 times 3 is 6, right? Same thing here. 2 times this quantity times 3 times this quantity. So 2 times 3 is 6. And then my personal opinion is if I've done an operation, I want to kind of cancel it out in the expression so there's less to look at. Maybe it's less overwhelming. And now I'm going to focus on the 2 radicals that have an nth root of 5. So I make the radical and I put a 5 there. Don't forget the nth root is 5. And now I'm going to multiply. So I know that 16 times 2 is 32. 16 times 2 is 32. And let's just take one step away from this problem here, and let's review multiplying when you have the same base, and you're multiplying. What do you do with the exponents? So my question is this a to the 5th or a to the 6th? What do we do? You have to know these properties of exponents to be able to apply it. When you have the same base and you're multiplying, you always want to add. You always want to add the exponents. So here I have a to the 4th, and here I have a to the 6th that I'm multiplying, same as over here. So 4 plus 16 is 20. Same thing, same base, and we're multiplying. 25 plus 5 is 30. So step 1 is I have taken the original expression, which is a radical expression, and I just rewrote it. That's step 1. The second and the last step is, can we simplify this? So there is a number inside. It's a large number, right? It's the coefficient of this. So I'm going to look back to the table, and I'm going to find the table that has n to the, or x to the 5th or n to the 5th, kind of depending on what your table was. So I'm going to look into this category that has, in my case, x to the 5th, and I'm going to find out, is there the number 32? So x to the 5th, again, why did I choose the 5? Because the nth root was 5. And I want to go down to see, do I see a 32? And if I do, okay, that means I can evaluate this and get a nice pretty answer, and the answer is 2. You may be thinking, like, I don't even get it. So let me I kind of made up a little bit of a story problem with my previous classes. Let's see if this helps. So 32 walks to the door, here's the door, and we're going to say, here's the bouncer or something, the security that's outside, and says, 32 says, hey, can I get through this door? And this n through to 5 says, yes, you can, because I know 32 to the 1/5 power is 2. That means if you take 2 times itself 5 times, you get 32. So I just evaluated the 32 out of this radical, and like I did above, once I've taken care of it, I like to cross it out so there's no confusion. Okay, using the silly kind of analogy here, A walks to the door, and A says, hey, can I get out? And the bouncer here says, well, the bouncer is 5, by the way. The bouncer who is 5 says, yeah, but let me see how many can I get out. So it comes over here and it looks at A, and he can see there's 20 A's, and he puts them into groups of 5. So you got 5 there. Why groups of 5? Because the nth root is 5. Got 5 there, and he counts how many groups of 5 can I put this into? A to the 5th, A to the 5th, A to the 5th, A to the 5th. Now, these 5s have to add up to 20. Whatever these are have to add up to 20. So I can see there's 4 groups of A to the 5th. So when A is let out and passes by the door, it gets evaluated into A to the 4th. And just like I was able to check and I said 2 to the 5th is 32, there's a way I can check that I did this right. 4 times 5 is 20. That means I did it right, okay? And I'm going to cross it out. Then B walks over to the door and says, hey, bouncer, can I get out? And the bouncer says, well, let me check. And so there's 30 B's. I'm going to put them in groups of 5s. 5, 10, 15, 20, 25, 30. Okay? 1, 2, 3, 4, 5, 6. Yep, I'll let 6 groups out. So 6 groups were let out. And the last thing I can do here to simplify is I know 6 times 2 is 12, A to the 4th, B to the 6th. Now before I ask you to give me your opinion on how well you understand that, I'm going to say that we're going to do another problem similar to this before we increase the strength. So let me just make up another problem. Give me 1 second. Give me 1 second here, okay? Yes, Brandy, that's another way to think about it. That's another way to think about it. So give me 1 second. So here's a similar problem, just like example number 3. I first look at it and go, okay, that we have the same nth root, so I can proceed. 3 times 5 is 15. And then I make this radical with an nth root of 3. I know 9, and I'm going to cross these out so I have less confusion. I know 9 times 3 is 27. Okay, now let's look at the a's. When you have the same base and you're multiplying, we're going to add. So 3 plus 4 is 15, and 20 plus 1 is 21. So again, we'll go with this analogy, and you can let me know if this analogy even makes sense to you after this problem. 27 walks to the door and says, hey, can I get out? And the bouncer, who's a 3, says, well, let me check. So we go over to 3 and we go, do we see 27 here? 27 is here. That means it evaluates to a 3. Yep, I'll let you out. So it comes out front, and now it turns into a 3. Okay, how do I know that? Because 3 to the third, 3 times 3 times 3 is 27. I just checked. It works. A walks over and checks, and A says, hey, can I get out? And 3 says, well, just a second, let me check. 3, because I have to do in groups of 3 now. 3, 6, 9, 12, 15. 1, 2, 3, 4. Oh, excuse me, you can't see that. 1, 2, 3, 4, 5. There's 5 groups. Yep, you can get out. So A comes out and becomes A to the 5th. And how can we check? 5 times 3 is 15. Okay, B comes out and asks the bouncer, can I get out? And B goes 3, 6, 9, 12, 15, 18, and 21. 1, 2, 3, 4, 5, 6, 7. Yes, you can get out. And he lets out 7 groups of 3. 7 times 3 is 21. 15 times 3 is 45. And Brandy, I'll explain after the next problem why I was not illustrating it with division. Okay, I'll explain that later. But if you understand that now, that's okay, Brandy, for you to use the division concept. So and this would be the simplified answer. Again, this learning objective was, can you rewrite the radical expression, and then can you simplify it? So this is not problem 3 or problem 4. I just provided you another one like example 3. Can you please go into the chat for me, and can you give me an honest one? What if the nth roots don't match up? You can't do anything, Elizabeth. Great question. What if these are not the same? Can't do anything. So everything that we're starting with right now and most of this chapter will always have the same nth roots. When you get into higher level math, you'll talk about what you can do at that point. All right, so can I have you right now as a 1 through 5 and how well you understand example 3 and this additional one? So it looks like most of you are giving 4s and 5s for your understanding. I just want to kind of preview and go, what's the difference now between what you just showed us and the last example, which is example number 4? Well, the difference is now instead of having numbers outside called coefficients that are whole numbers like 2 and 3, now I have fractions, that's 1. And the second difference you're going to see is when I had to list this 20 in groups of 5, so I did list in groups of 5, or I list this 30 in groups of 5, or I list the A's, so A to the 15 in groups of 3s, or B's in groups of 3s. This time, the number at the very end is not going to end in a whole number of 3, or is not going to end in a whole number of 5. There's going to be leftovers, and we're going to learn what do we do with those leftovers then. Okay. So how do we multiply fractions? We multiply straight across. 2 times 1 is 2. I'm going to just write it down really small. And 3 times 4 is 12. And the reason I'm writing it down small is because you're my third class of the day, and I know that this can be reduced. 2 goes into itself, divides into itself 1 time, and 2 divides into 12 6 times. So 2/3 times 1/4 reduces to the fraction of 1/6. Okay, and myself again, I think it's helpful to cross it out. And I've already looked to see that we're working with an expression has the same nth root. So I already knew that in advance, even though I did not state it. 3 times 27 is 81. And I know that a to the 5th times a to the 6th, same base and multiplying. I keep the base the same, and I know 3 plus 6 is 11. I said 3, I meant to say 5, excuse me. 5 plus 6 is 11. And b to the 11th and b to the 12th, 11 and 12 would be 23. Okay, so 81 walks to the door and says, hey, can I get out? And the number 4 says, well, just a second, let me see. So again, I go to 4, column 4, and I go down to see, is there an 81? Oh, there is. That means it evaluates to be 3. And so the bouncer says, yes, you can get out. And when it gets out, it becomes a 3. Now A walks to the door, and A says, hey, can I get out? And bouncer 4 says, well, just a second here. And so the bouncer comes off to the side, and he's going to write them in groups of 4. And so it's like, there's 4, there's 8, right? Excuse me. There's 4, there's 8. And now, once I get to 8, I can see there's only 3 left to get to 11. So I don't have a whole number of 4. That's the issue with this example. So there's only 2 groups that make a full 4. So remember, 4, 8, 11. 4 plus 4 plus 3 is 11. So 2 groups get to come out. 2 groups get to come out. And he says, all right, I'll let out 2 groups, but there's 3 remaining. And those 3 need to stay inside. And you definitely may be wondering, like, how do I know if I did this right? 2 times 4 is 8. 2 times 4 is 8. Plus remainder of 3 makes 11. B walks to the door and says, all right, bouncer number 4, can I get out? And just a second. So he comes over and he goes, okay, there's 4, 8, 12, 16, 20. Oh, I can't do 24. That'd be too much. I can only go to 23, so it has a remainder of 3. So 4, 8, 12, 16, 20, and then this is the 23. So the bouncer says, I'll let out 1, 2, 3, 4, 5. Let me make sure I count that right. 1, 2, 3, 4, 5. I'll let out 5 of you. There's 5 full groups, but there's not enough here to be let out. Must stay inside. How can I check to see if I did it right? 5 times 4 is 20, plus 3 is 23. And the last thing we have to do, remember, we rewrote it here, or you watched me rewrite it, and then I'm simplifying it. So the last thing I need to do is simplify the numbers out front. 1/6 times 3. A common misconception is students think the 3 should be multiplied by the top and the bottom. No, only ever it gets multiplied by the top. 1 times 3 is 3, with the 6 in the bottom, and this reduces to 1/2. 3 goes into itself once, 3 divides into 6 twice. So this final answer is 1/2 up front, then a squared, b to the 5th, make that 4 small, so the 4th root of a cubed, b cubed. That is the hardest learning objective I believe that you're going to see today. Can you do me a favor? Can you go into the chat and can you provide me right now with, be honest, with a thumbs up if you were not timed? I think I could attempt a problem like that. Like, I think I could attempt it. Or a thumbs down. I'm feeling too confused that I could do that independently. Thumbs up or thumbs down before I look at the third learning objective. Thumbs up or thumbs down? There is no tutoring on Friday mornings. Just so you know, there is no tutoring on Friday mornings. We are going to move on right now to the third learning objective. And this learning objective is going to be, again, that we're going to rewrite the radical expression, but these radical expressions look different. They don't have any variables in them. We're going to rewrite them. The table is going to play an integral part in doing this. And you may be thinking, like, well, why do I have to rewrite it? And here's the reason why. If you're struggling, I suggest, again, that you go back and watch the video that I'm going to provide you with, and then reach out to me for additional help on problems if you need it, okay? I'll be happy to help you. So why do you need to rewrite this? Well, let me show you an example. Let's say you did some math and you got this as a final answer. And you turn that in. You're in this class, you're in pre-calculus, and calculus you're in college, you turn this in, you're like, I know for a fact that my final answer to a problem equals this. It's very possible that your professor or your teacher says, yeah, I'm going to count it wrong. And the reason is this is not proper. Just like if you were going to write a paper or type out a paper for your English class, your teacher would expect that you punctuate, that you capitalize the first letter of a statement, of a sentence, or of a question. And same in math. I don't know who makes up these rules, by the way, but the rule is that your final answer should not have a radical on the bottom. This may be the right numerical value, but they don't want us to write it like that. They want us to find a way to rewrite it so I see no radical on the bottom. So here's what we're going to do. This right now covers both numbers. It means it's shared by both numbers, so I'm going to rewrite it on top, and that should be a smaller 3, that's my mistake, and a smaller 3 in the bottom. So again, it's just being applied to both. It's over the top of both, so I apply it to both. My whole goal is to keep the value of this the same. It's like if you put this into a calculator, that answer better be equal to the same answer I get at the very end. They're going to be equal, they're just going to look different. And so to do that, I look at whatever the nth root is, and then I look at this number. I look at the nth root and then this number. Okay? So the nth root is 3. So I find column number 3, and the number was 108. So 108, okay, where's 108? It's right here. It's in between 64 and 125. And you're welcome to use a decimal calculator for this. And so I take, again, 108 is right here. I take the next number, and I divide it by 108. If it's a whole number, awesome, that's what I'm looking for. If not, I keep going up, one by one. 216 divided by 108. Oh, there we go. I just found the answer. I know 108 times 2 is 216. So I'm going to extend the radical on the top and bottom, and as long as I multiply the top and the bottom by the same number, it doesn't change the value of this fraction. So 5 times 2 is 10, and 108 times 2 is 216. You still have a radical on the bottom, Miss Bradley, like that, aren't we supposed to get rid of that? I'm going to, in just a second, I'm going to go to the column that has a 3 and find 216. Column of 3, find 216, go straight across, it evaluates to 6. So this final answer is 6 by itself on the bottom. There's no radical, it's gone. There is the nth root is 3 here, of 10. This would be the final answer. If you plug this into the calculator and you plug this into the calculator, they'd be the same decimal answer. We just rewrote it. We no longer have radicals on the bottom. Okay, let's go on to the next one. And a question that a student had in the previous hour is, how do I know when I have to do this? Well, again, this is going to be applied to the top and bottom, so I'm going to rewrite it. Applied to the top and applied to the bottom. And you know you have to do it when, let's go to the 4th column and see if you see a 4. 4th column, there's no 4 here. That means I need to do it. So I need to find a way to, it's called rationalizing the denominator. So let's figure out what that number needs to be. So I find where 4 is. It's that inside number in column 4. It just happens to be the same number for this particular problem. Here's column 4, and 4 would be right in between 1 and 16. And I just go one by one, working my way down the list until I find a number that works. And we just happen to get lucky here. Like, for instance, if I did 81, 81 divided by 4 is not a nice whole number, but I should start always with what is the number right after. So the first number after 4 in this list would be 16, and we can see it works. It just happens to be 4. So I'm going to take the top and bottom by 4. And now when I go to that list and I find a 4, list 4, and I identify the 16, there's list 4, identify the 16, I go straight across and I get an answer of 2. This is my final answer. A really common mistake is that students, this is not correct, but students want to write, okay, well, 12 divided by 2 is 6, so I think this is my answer. These are not like terms. It's like telling me that you could take 6x and add 2 to it. It doesn't have an x. You guys know that. You can't combine them. You can't combine this. One of them has a radical, one of them doesn't. I can't divide them. This is my final answer. Can you go into the chat right now? Into the chat. Give me 1 second. And can you give me right now a smiley face or a frowny face? Thank you again for the honesty in your feedback. A smiley face or a frowny face if you would feel comfortable attempting problems like this on your own right now. Smiley face, yep, I think I could do that if time is not a factor. A frowny face is I'm really confused what you're doing. Okay, thank you for the feedback. We're on to our last two. So our last two is we are going to rewrite this. Okay, we're going to rewrite both of these expressions that contained radicals. We're going to rewrite the radical expressions. And remember, our final answer, we don't want to have a radical on the bottom. Now, I'll tell you, these two problems really rely on Desmos. If you had a graphing calculator or any kind of calculator, you throw that calculator down, it's going to do the work for you. Pay close attention. Remember, when you have the same base and you're multiplying, you add the exponents. Well, how do I add these exponents? What does it look like? Well, there is a 1 here. Even though you can't see it, there's a 1 here as an exponent. So really, if I rewrite this like you learned in yesterday's video, this is 1 over 20. Again, same base and multiplying, I add the exponents. Plus 3 over 5 plus negative 1/10. What's in the bottom? X to the 1/4. So I'm going to go into Desmos right now. I'm going to pull that up into Desmos. And I'm going to type this in using parentheses. So 1 divided by 20 plus 3 divided by 5 plus negative 1 divided by 10. Oops. There we go. And I don't want to use decimals. I want to use fractions. So if I come up here and I hit this little fractional key, Desmos did the work for me. I didn't have to find a common denominator and do all of that stuff that takes time. I know that these three values combined is equivalent to 11 over 20. Let's review the properties of exponents once again. Same base, and we multiply, we add the exponents. What do you do when you have the same base and you're dividing? You subtract, and the order you subtract is just top, subtract bottom. Same thing applies. Could you do this by hand? Sure you could. I think we can save ourselves a little bit of time, and we can use Desmos to do it for us. So now I'm going to take that top exponent of 11 over 20, and I'm going to subtract 1 divided by 4. Again, I'm going to turn this into a fraction by coming over and hitting the fraction key. And this tells me that this expression, after I reduced it, is equivalent to x raised to the 3/10. X raised to the 3/10. Give me a 1 through 5, please, right now. 1 through 5, and how well you're able to understand how I applied properties of exponents. It's almost foreign. It's like its own little rules and language. Maya, I just saw for your last problem, you cannot reduce that any further, Maya. I just saw your question for can we reduce the previous problem up here, Maya? Nope. These are not like terms because this does not have a radical on the bottom. This 3 should have been written, I should have been a little neater. This nth root should have been a little bit smaller. There's nothing there you can do to reduce it. Good question. Okay, let's look at the next one. See if I can zoom in here. Okay, same thing. Same base, and we're multiplying. So again, this has a 1 here. So at your top, your nth root is always on the bottom, regardless if it's smaller or larger. Plus negative 3/5 plus 9/10 divided by 1/8. Simply how you're going to show your work as well. So I write it out. Then I move into Desmos. And I have 1/4 plus negative 3/5 plus 9/10. Okay, again, I like to use fractions, especially since they don't scare me as much, or they may not scare you as much when you have this calculator in decimals. So this is equivalent to 11 over 20. Just happens to be coincidence. It's equivalent to the same thing. So this is 11 over 20 over 1/8. When you have the same base and you're dividing, it's always going to be, let me move this up for you a little bit. It's going to be the numerator subtract the denominator. When do you do that again? When you have the same base and you're dividing, it's top subtract bottom. I'm going to let decimals do the work for me. So I take the 11/20 and I subtract the 1/8 and I turn it back into a fraction by clicking the fraction key, and that will be my final answer. Now I want to go over again a common mistake. It's a good opportunity to talk about it. So a common mistake is people say, oh, the answer is, I got to go back, I think it was 17 over 40. Yep. Okay, so a common mistake is students say, the answer is 17 over 40. That's my answer. No, that's the answer that I want to place in the exponent. The final answer is x raised to the 17th over 40. That's my final answer. All right.